Yeah. Okay. Uh, You're just auditing the class. That's funny. Uh, mm. Man. How do I get rid of this trash? Yeah, you can see that. Okay. Okay. I guess we're ready. Are you recording? And so I need to stay out of. Oh. Okay. Right here, right? Right there. So just stay out of here. Right. Okay. I think we're finally ready. Hi. Oh, you're listening to me? Oh. Oh, okay. You guys got this stuff down. Okay. Well, I promised this for about a year and a half, I think, and the guilt got so high that finally I said, let's just do it and do it extemporaneously and stuff. But okay, so we're going to talk about electricity 101, and so let's start. Uh, this is a model of an atom, very simple, and you all know that. We got protons in here, and I'm not showing the neutrons. And around the atom we have electrons. And the electrons are the workhorse of all of. There's the workhorse of the universe. The number of things that happen because of electrons. And so let's talk about what is a proton. A proton has mass. It has mass, and it's 1.672 times 10 to the minus. Yeah, and I'm using red for positive. Okay, on here, red is positive, green is negative. So a proton. Here's a proton with its mass. Okay, a proton also has charge, electric charge. That has everything to do with electricity. Is the fact that this proton has a positive charge, and it has 1.6 times 10 to the negative 19th coulombs. Okay, you don't need to memorize that, but these are in coulombs, Coulums. And the coulombs is a measurement of charge, of electric charge. So it has mass, and it's got a positive electric charge of 1.6 times 10 to the minus 19th. Now, an electron also has mass, and its mass is 9.108 times 10 to the minus 28th. Now, notice how much lighter an electron is compared to a proton. Wait a minute, I didn't do this right. It's right here. right? 10 to the minus 28 is the mass. 9.1 times 10 to the minus 28 is the mass of the electron. And look at the mass of the proton. It's only 10 to the minus 24th. So this is 10,000 times lighter. 4 orders of magnitude, right? Minus 24 zeros versus minus 28 zeros. You see what I'm saying? So these electrons, as far as mass, are 10,000 times lighter than a proton. Mass. But notice charge. They both have the same electrical charge. Positive, negative, but the amount of charge is the same. Isn't that interesting? And they're exactly the same. So a proton is 10,000 times heavier than an electron, but both of them have the same amount of charge, but in the opposite direction, positive versus negative charge, of 1.6 times 10 to the 19th, 1.6 times 10 to the minus 19th. Just something interesting, to observe. Now, our electrons have another characteristic. They have what's called spin. And don't think of it like a sphere spinning around an axis. They labeled it spin, but does anybody know what spin relates to? What physical phenomena spin relates to? You should know, but you're not going to answer. What's that? Not gravity. Good try. What are the other forces? That's still gravity. What are some of the other forces? Well, that's it. Yeah. Magnetism. Spin relates to magnetism. An electron can have either left spin or right spin. And that's how we get north and south poles on a magnet. So with electricity, magnetism plays a big role when we get into motors and generators and transformers. But so these are the properties of an electron. Right? And so the charge part then is the electric charge, and that's measured in electron volts. And that has everything to do with electricity. The charge on an electron has everything to do with what we call electricity. And the amount of charge is measured in volts. You'll say an electron has, when it can be 2 million electron volts. That has to do with how much energy is in that electron. So, okay, so now, are you with me there? Now there's four key quantities that we need to think about regarding electricity. The first one of those is voltage. V-O-L-T-A-G-E. Voltage. What is voltage? Voltage is a measurement of how much charge or energy there is on the electron. That's what it is. Voltage is a measurement of how much charge is on that electron.
Can you clarify?
What's that?
Each electron only has a specific charge, so wouldn't it be multiples of electrons that are generating higher charge?
No, each electron has a charge level, and that's what voltage is. Yes. Every single electron carries this much charge. And charge is going to turn into current.
Yeah.
Well, charge moving,
Yes.
electrons moving, is going to turn into current. But voltage is directly related to how energized that electron is. How much energy is in that electron. Okay? So it's a measurement of how much charge or energy an electron has. And so an electron, think of it this way, an electron is a little energy storage unit. Think of it that it's a little energy storage unit. And it's measured in voltage. That's voltage. Okay, amperage. A-G-E, amperage. Now, amperage is a measurement of the flow of electrons in a conductor. Now, we need to illustrate that. Let's see. All right. There's a nucleus. Okay, these are atoms in a conductor. Okay, let me draw 3 of them here. Okay, and we got these little guys, and we're going to now learn what current flow is. Okay, let's do it here. Okay. Okay, so these are 3 atoms. Okay, now in your conductor, you've got trillions of these. These are 3 atoms. So now what in the world is current flow? Well, these guys are negative, okay? So if I put a big positive charge here, I come over here and I got a great big positive charge against this atom. Now, what's going to happen is, if I get this positive charge strong enough, this electron, now these electrons are held by the protons, correct? In other words, positive attracts negative. So these guys live around their nucleus because this positive attracts this negative. So that force keeps these electrons with this nucleus. But if I come over here and I create a positive force here, stronger than the positive force coming from this nucleus, these guys pop off. They pop off of this atom. And those electrons come over here. Now, what happens to the net charge of this atom is what? When it's balanced.
0.
That's correct. When I have the same number of electrons and the same number of protons, the net charge is 0. Okay? But when I go and put a positive charge against these atoms, these electrons pop off and come over here. Now what happens to the net charge of that atom when I pop off these electrons?
Negative.
What's that?
It turns negative.
Flip, it turns positive. I pop off the electrons, so now I've got, say, 20 protons and 18 electrons. I'm 2 plus on the protons. So I've got 3.2 coulombs of charge. And so now this atom is suddenly positive, and what does he do to his neighbor? He pops off these guys. He pops off 2 more electrons. That's current. That's flow of electrical current. It's all these electrons popping off to their neighbor. That's what current is. And that's why we say flow. Okay? It's just it's electrons jumping from atom to atom to atom. Everybody got that? That's what electrical current is. Okay? So amperage then is a measurement of how many electrons are in this pop-off mode, how many electrons are flowing per second. That's what amperage is. Amperage is a measurement of how many electrons are moving through that conductor. So, all right. So I did, yeah, and I think we'll use V for voltage, and amperage. We can use either A or I. I don't know which to use. Often, let's use I. I for current. Okay. So that's voltage. That's amperage. Now our next quantity that's important is wattage. So is wattage. Now, wattage is a measurement of power. Okay, so this is a measurement of power or energy. That's what wattage is. So let's remove this. So now we're talking about wattage is power. Now, the power and energy, those are synonyms. When we're talking about power, we're talking about wattage, we're talking about energy. See, so far we've just been talking about individual electrons. They each have energy. So where is the energy in the system coming from? The energy in the system is coming from that these electrons, every one of them, has a quantum amount of energy. And so if we move electrons, we're moving energy. So, and we want to be able to measure how much energy what's going on in our system, how much energy are we using, generating, or consuming, and all of that. So wattage is a measurement of energy, and so wattage equals voltage times the current. Okay? So you see, one thing I didn't say on amperage, I should have said it. 1 amp, this will impress you. What we call 1 amp, okay, equals 6.24 times 10 to the 18th electrons per second. So when you, that's right, when you flow 1 amp through a wire, you are moving 6.24 times 10 with 18 zeros. That many electrons are doing this hopping game. That's 1 amp. Okay? So now each one of those electrons has some energy, correct? So, and the energy of that electron is based on the voltage. How energized it is the voltage. So power is the voltage, which is how energetic that electron is, times the current, the number of electrons that are moving. Right? Each electron has a little bit of energy, and so that little bit of energy times the current is power. That's how much power is being moved in the system, or energy. You good with that? Okay. All right. So that's wattage. And so we have wattage equals voltage times current. Okay, resistance. Our fourth thing is, let me just put this over here. And W equals the voltage times the current. Okay. And our fourth thing is a little more difficult, and is the resistance. So resistance is a measurement. A measurement of material is the material's resistance to current flow. See, when we had our example here of electrons hopping over to, well, different atoms have different amount of resistance. In other words, let me get our atom back up here again. Okay. Okay. So we come over here and we put our positive, our positive source here, and we start out, we put 10 volts. Nothing happens. No, I'm not leaving. In other words, it's resisting current flow. 10 volts, no electrons pop off. 100 volts, no electrons pop off. 1,000 volts, oh, okay. Boing, boing, they start to pop off. So that's resistance. Resistance is resistance to the flow. And some materials have very low resistance, and those are called conductors. So a conductor is a material that is very low resistance. Some materials have very high resistance, and those are called insulators. So insulators have very high resistance. You put 10,000 volts there, nothing moves. But all materials ultimately are conductors. If you put enough potential, you can strip those electrons off. That's what lightning does. Air is an insulator. Well, air has a high resistance, but when that static electricity in the cloud gets to a voltage high enough, air will conduct, and that's called lightning. Okay? So resistance is this resistance to the flow of current. All right. So, given those things, we can. Let's see. What else I want to say about that? No, I think I said all that. Yeah. And about what are some conductors? What copper? What about silver? Is it a better conductor than copper? It is. What's better than silver? Gold. Right. Gold's a very good conductor, but it's very expensive. What's not as good of a conductor as copper, but often can be used? Aluminum. That's right. Yeah, it's not as good of a conductor. It has more resistance. Aluminum has more resistance than copper, and so forth. Right. Now,
what do they use on the inside of resistors?
What's that?
What do they put on the inside of resistors? Like what material?
On the inside of what?
A resistor.
Oh, often carbon. Yeah, like an electronic component is called a resistor. Okay, and oftentimes they're carbon, and so if you have very little carbon in there, it's a higher resistance. But if you have more carbon, it's a lower resistance. And I should have said the unit of resistance is called ohms. It's OHM, okay, is a measurement of resistance in ohms. That's the guy's name. Ohm is the guy, it's named after the guy that developed the concept of resistance. So, yeah, and when you build electric circuits, oftentimes you use resistors to control current flow. So you want to control the flow of current, so how are you going to control the flow of current? By using resistors to get the amount of current you want. So, but we're getting into electric circuits, and that's not what we're doing here. But so this is the basic things. These four categories, the basic physics there with the electrons and protons and that type of thing. So just with that, we can do a lot with that. So there are a few basic equations.
You could just start a new page if you wanted.
I know. Yeah, maybe I should do that, huh? Yeah, yeah. Let's do that page. Yeah, that's a good. Yeah, that's a good idea. Okay, so here we go. You know, every electricity 101 in any college is drum roll Ohm's law. Okay, Ohm's law. You got to master this. Okay, so we have some varying equations, and so we have I, which is current. So maybe I should give the concept of a circuit first. You know what? Let's do the concept of a circuit first, and then we'll do the equations. So there's a difference between static electricity and then actual current flow. So when you walk across your carpet at home with plastic shoes, the right kind of soles, and you walk across there, and you think nothing's happening, and then you get close to a negative, a ground, whoa, you get shocked, right? What's going on? What's going on is by your scuffing your feet like this, you're energizing these electrons. That's what you're doing. You are energizing your body. Your electrons in your body they're energizing up. They're getting higher and higher voltage.
Higher negative or positive?
Positive, I think. Positive. You're getting up to thousands of volts. And it's called static electricity because it's not moving. There's no electrons jumping from atom to atom. But suddenly, you are this plus charge here. That's you, and you've charged yourself up with a positive charge into the thousands of volts. And so when you get over to the ground, which is a negative, you don't even have to touch it. If the room is dark, you'll see a spark go through the air into the ground. That was current flow. All of those charged up electrons. So static electricity, it's not moving. The electrons aren't moving. But an electric circuit, okay, so let's put, let's say this is a battery. I think that's the symbol. Is that the symbol for battery, David? What is it?
Just like that, but just like two.
Oh, just like two?
Small line, big line.
What's the right symbol? Oh, I got to get the right symbol for a battery.
Small line, big line, small line.
Big line, small line, big line, small line. That's the symbol for battery. Now, which is the positive or negative, the big line or the little line? Let me draw this again. Big line,
You can just do it, yeah.
small line, big line, small line. This is positive, the big line? Okay, so this is positive, all right? So we have a battery here, we have a wire, and we come over here to, we'll call that a load of something. You know, maybe this is a heating element in the space heater. You can relate to that, right? Let's say that's a heating element in the space heater. And so we come over here like this, come over here. Oh, let's put in a switch, okay?
After that, you can also put a circle with what's it called, like a plus and negative. That's also easy. I think that's easier than that.
What's that?
Circle plus and negative, but it's either or.
Okay. Okay, this is a switch. So we have a, let's say we have a 100 volt battery, and the switch is open here. Is anything going to happen? No current's going to flow. Okay? But as soon as we close this switch, connect this switch, now we've got a positive charge over here, and we've got a negative charge over here. So guess what's going to happen? Current's going to flow through the circuit, right? Now, which way does it flow? Does it flow out of the positive terminal? No, it's gonna flow this way. Yeah, the electrons flow in. Current flow is going to be this direction. This positive is going to attract this negative. So the electrons are actually going this way. So in your car battery, the electrons are going into the positive on your battery. Everybody thinks they're coming out, but they're going in. Now that is called current. This is a circuit. It's a complete circuit. And so what's going to happen is this current's going to flow until this battery goes dead. And the dead battery means there's no difference in charge from the plus to the minus. And when there's no more difference in charge, no more current flow. Okay? So that is a circuit, a closed circuit. Okay? And if the wire's broken, it's called an open circuit. So that's current flow through a closed circuit. Now we can go to Ohm's law about these circuits. How do we understand these circuits? All right. Okay. So current equals voltage divided by resistance. So the amount of current that goes through that circuit, how many electrons are blasting around through that circuit, is the voltage divided by the resistance. Remember, the resistance resists current flow. So notice, think about this equation just for a moment. If you increase resistance to the flow of current, what would you expect to happen? Lower amperage. If you increase resistance, you're going to have lower current. That's what resistance is. Resistance is resistance to all those electrons popping off. So if you increase resistance, you lower current, which is this equation shows you that, right? When you increase you're dividing by here, what's that called? The denominator? The denominator, when you increase that, that's going to lessen current. But what happens if you increase voltage? It's going to increase the current. So when you increase voltage, you're going to increase the current. Increase resistance, you're going to reduce the current. That comfortable with that? He's thinking about it. Resistance resists current flow. So if I increase resistance, it's going to result in lower current in my circuit, given the voltage remains the same. Given the voltage remains the same, if I increase the resistance, the current's going to go down. Okay? All right? So, from this equation, we can also then know resistance equals, in my circuit, resistance equals voltage over current. I should have gotten used to using this thing. So resistance then, that's I. Resistance equals voltage divided by current. Right? So that's coming out of this same equation. We just solved it for resistance. Okay? So if I want to know the resistance of my circuit, what I'm going to do is measure the voltage and the current, and I can compute what the resistance is of my circuit. All right, now, let's do this. Voltage equals current times resistance. Okay? Voltage equals current times the resistance. For instance, let's do a little different circuit to illustrate that. Let's say instead of a voltage source, we have a current source. This is a little more challenging. But remember our first circuit, we had a voltage source, right? In our first circuit up here, we had this battery, right? And we said this is a 10-volt battery. So this is over here, goes to our load, comes back into this battery here. We had a voltage source. So we're assuming it's an ideal voltage source. It can pump out as many amps as it wants. It always is 10 volts. So, but we could have a different kind of a circuit. Instead of having a voltage source, we could have a current source. And so our current source knows, okay, our current source knows how to pump out electrons. And so we want to say 2 amps. Give me 2 amps on my current source. So that's going to pump out, how do I go back here? Is this how it goes back?
Slide the other one to the right a bit and then find the other one.
This one?
Yeah, slide that to the right and now go grab the other one. On the bottom.
Oh, there we go. Right. So remember, we said 1 amp is 6.24 times 10 to the 18th electrons. So we have a current source. And so this guy pumps out 12.48, okay? 12.48, right, times 10 to the 18th electrons. So our current source is going to pump that many electrons out.
Would you mind giving an example of each in real life or where we would use it or how they're used?
Current sources are not as common as voltage sources. And I'm trying to think of a concrete example of where you would want a constant current source. I'm not sure. David, do you have where you would use a constant current source?
Oh, no, not really. They're really rare.
Okay, but I'm driving to a point to illustrate this equation. So the question is, so the question is, on this circuit, how much voltage needs to be produced in order to do this? So this equation tells us the voltage equals the current times the resistance. So if I have a resistance here of 10 ohms, and I pump through it 2 amps, I can compute the voltage. See, I'm pumping 2 amps, I got 2 times the resistance is 10, and so that's going to equal 20 volts. See that? That's how it works. So if I know the resistance and I know the current, I can determine the voltage. So, okay. We'll have a concrete example coming up here that'll pull a lot of this together. So that's voltage. Okay, now let's talk about energy, wattage. Let's see. Do I need this? Yeah. Yeah, let's get rid of this. Let's get rid of this. All right. Voltage. All right. Wattage equals. This is a measurement of power. It's going to equal our voltage times our current. Did we already do that? No, we didn't do that. Okay. So the power is the voltage times the current. Now, think about this equation for a moment in regard to the physics of our electrons. You see, remember, the voltage is a measurement of how much energy is in the electron. Current is a measurement of what?
How many electrons are moving?
That's correct. So the voltage is how much energy in each electron, and the current is how many electrons are moving. And so when you multiply these two together, you get how much power you have moved. Every electron has a little power, and you're moving them somewhere you want to do something with them. So wattage then is how much energy is in that electron and how many are moving. So if you increase the current, you increase the wattage. If you increase the voltage, you increase the wattage. Okay? Okay. So there we go. You could derive one other little formula from this relationship right here. You could come up with what? Current equals the wattage divided by the voltage. That comes useful sometimes. Okay? Current equals the wattage divided by the voltage. All right? So those are your basic, the math doesn't get any more complicated than that. It's those basic relationships, and that's all tied back into what an electron is, that it carries charge and that electrons can flow. And electrons carry energy, so that's how energy comes into all of this. You guys good? All right. So we're gonna do a fun problem here. Oh, I'm sorry.
No, we're good. I'm stretching.
You're good? You got to keep me on the straight and narrow. I haven't thought about this stuff in a long time.
A common current source would be like a current transformer.
A what?
A current transformer is like a current source. Yeah, that's like a really common current source. That we see.
What kind of transformer?
A current transformer.
A current transformer.
You have a voltage transformer. You have a current transformer to measure power consumption.
You have it hooked around a feeder or something, or a bucket.
Oh, you mean like a toroid? Aren't those called toroids?
Yeah, well, basically they're towards
We just call them CTs.
yeah, current transformer.
And you put that to measure the current,
Because it induces.
You know, you have the
right? Oh,
yeah, it's a
does that induce that induces a current,
yeah, electromagnetic.
right?
Yeah, and then you have like the windings of the thing is dependent. Like if you have a 10 to 1, that's like if you have like a 1 to 10 current transformer, it transforms like 1 into like 0.1 amp.
Yes.
That's the current source that we see often.
That's interesting.
I never thought of it as a source.
Yeah, I don't know that that's a source. It's a current transformer, and what you're doing, the alternating current in the wire is inducing a current in the toroid, and then we're measuring that. Oh, but what do they measure? They measure the current flow off of that or voltage? They measure the current flow off of that, right?
No, that's basically like a current source that we use it. Like you basically know the voltage, and then you you often use it in like power meters to detect the power consumption.
But what I'm asking is, what is the power meter measuring when you connect that toroid to the power meter? Are you connecting it to the voltage meter or to the amperage meter?
To the well, you have the actual load, what's it called, the wire.
Yes.
The actual,
Yeah, let me bring these other guys along. What we're talking about here is we have this conductor,
yeah.
and we have this conductor, and we have current flowing through this. We have alternating current flowing through this, and this device called a toroid. See if I can I can draw one. It's a coil. It's a coil of like this. Is it? We're getting in here too deep. Is it connected?
No.
No, it's not.
It's just like you can imagine like a lot of
Right, and we come off of here, right? It's a lot of windings. And where do these go? What do these connect to?
well, I don't think that's exactly how it goes. It goes like it's just like a toroid, but you put the actual current through it.
Oh, this is. You're saying you induce a current through this? No. Yeah. What I think will happen is you'll put some kind of a load here. This will connect to probably a resistor, and so this is wrapped around this. Okay, this is wrapped around this, and this current flow causes a current flow in this little wire, and then there's a resistor here, and then do you measure it? With your voltmeter measures that, correct?
Yeah.
Is that how it works?
Not exactly, but yeah, something like that.
Right. So I don't know that this is a current source. Well, sure. I mean, it works. Well, that's how that's going to work. Now, in order for this to work, we need, what was that one other thing we said electrons have? Having to do with the spin? Magnetism. The only reason this works is because of magnetism. Magnetism is in play here because there's no physical connection from this wire that's all coiled around to this. There's no physical connection between them. And yet this alternating current through magnetism introduces a current flow in this coil. So we're getting into transformers. We're way beyond. Who made? It's David's fault. He brought this up. No, that's okay. Okay, so here is a problem. I got two problems now. All right, let's go over here. We got two problems. Problem number one. Here we are. We have a I'll do it this way. We have a 240 volt source here, okay? 240 volt source. All right? And we are going to connect that to a how do I draw a motor? There's proper symbols for all of these, which I don't remember. That this is a motor. Okay? So we got a 240 volt source on a 240 volt motor. Okay, and this is a 2 horsepower motor. Okay? This is a 2 horsepower motor. Now, how big of a wire do we need to use? What gauge wire should we use on this? Now, let me give you a hint or two. Okay? So, horsepower is another unit of energy. Wattage is a measurement of energy. Horsepower is a different kind of measurement of energy. Does anybody know how to convert horsepower to wattage? You should know this. Okay, so one horsepower equals, I think I got it, 746 watts. Okay? So 1 horsepower equals 746 watts. So I got 240 volts. So how are we going to figure out what size wire we need? Well, what do we need to figure out first? That's correct. We need to figure out how much current. We know the voltage, and we know the wattage is what? The wattage is 2 times 746, right? For our motor. So we know the wattage is, what is it, 1480 plus 12, 1492. Did I do that right? We got 1492 watts. So we know the wattage, and we know the voltage. So we should be able to compute the current. We know the wattage and we know the voltage. So current is equal, we go back to our formulas, and current is equal to the voltage. Current equals voltage divided by wattage. Do I have that right? I think I do. No, I got it upside down. Current is equal to, the wattage divided by the voltage. Yeah. It's okay if you have your little cheat sheet. Current is the wattage, right, divided by the voltage. Yeah. So what's our current going to be? Our current's going to be 1,492 watts divided by 240. And what's that equal? 6.2 amps. So that's going to be 6.2 amps on our circuits. Now, what size wire you need, the other thing you need to know is the wire table as far as conductors. So what's the abbreviation that they always use in front of the numbers? Gauge, but what's the AWG, right? AWG means American Wire Gauge, G-A-U-G-E, okay? Known as AWG. So we don't have all of these memorized. Good electricians have them all memorized. I'm joking. I know. Let me guess. You got 12. What's the rating on an AWG 12? 12 amps. No, this is AW12. What's the amperage rating? That's correct. AW12 is 20 amp rating. Okay, what about an AWG 14? That's equal 15 amp rating, right? Okay. So will a 14 gauge wire work? Well, sure. We're only pushing 6.2 amps, so a 14 gauge wire will work. A smaller wire will work than that. You know, a good engineer doesn't over-engineer.
Well, you have problems, right? I think if you use too big of a wire, you have some problems.
Nope.
Oversize those a bit.
No, yeah, you can oversize as much as you want. You waste a lot of money, but there's no problem.
Your conduit fill and everything becomes an issue.
Well, yeah. I mean, if you use bigger and bigger wires, just lower and lower resistance.
But I thought devices on the end, if they're too big, they can wear out if you oversize the wires too much.
Nope. Oversizing the wire just delivers. There's some resistance in this wire, So like if we put our voltmeter, if this is our if this is our voltmeter here, and we came and measured here, okay, and we measured, and we measured that, and we got 240, say 0.000 volts. What would happen if we put our voltmeter over here? We measured here and here, and let's say this was 100 feet. So what voltage would we read over here?
You can voltage drop, but depending on the size of your wire.
Yeah, it won't be the same. It'll never be the same unless you have a superconductor that has zero resistance. So that is correct. If we could make this more complicated and say, well, let's say we're going 10 miles. Okay, what size wire do we need to go 10 miles? Well, how much voltage are we going to lose? And in order to figure that out, we need to know the resistance of the wire. But with these formulas, knowing the resistance of the wire, you can compute all of that. So the answer to my question is, this is going to be like 239, maybe 0.5 volts. And the reason we've dropped is because the wire has no resistance. Now, if we put a much bigger wire in there, this is going to approach 240. The bigger wire we put, the closer this is going to approach 240. But no, oversizing, you can oversize the wire as big as you want, and it's not going to have any negative effect. Yeah. What's that? Well, until you try to pay for that wire and how costly that copper wire is.
Nowadays it's really expensive.
Yeah. So we're applying, all of Ohm's law to this, and so once you know these principles, you can figure all kinds of stuff out. So I have another problem, another sample, and we'll end with this. Is let's say, let's move this over. All right. Let's do another problem. We're designing a space heater. Okay? We're designing a space heater, and we have a 110 volt supply is our power source, and we want our space heater to generate 1,500 watts of heat. Okay? So our circuit is pretty simple here. We have the supply again. It's the 110 volt supply, and we're going to run that into our space heater, and we'll use a symbol of a resistive element. So this is a symbol of a resistor. Okay? That's a resistor. And you're designing this space heater, and you need to order the resistive element, and you need to tell them how many ohms. What resistance element do you need in order to do this? So you're designing the space heater, and you got to order that. So you're going to think about how to compute that, and I'm going to go use the restroom and figure out how many ohms that needs to be. Okay? could go through our program.
So I'll just send you that about Chris and Ginger Brown.
Hold on a
You
second.
guys' number. I have.
Oh,
our
let me
number.
mute this thing. First we'll compute the current, and then we'll compute the resistance.
So in basic, okay.
So do we have an answer?
8.1 ohms.
What's that?
8.1 ohms.
That is correct. 8.06.
I got 8.066.
Yeah.
I got 8.088 something.
Okay, well that's how many digits of precision. There you go. So now you can place your order for your resistive element.
Would you do a single resistor valve at 8, or would you do multiples
The-
strung together?
I have no idea, but okay, so there you go. I think that pretty much concludes today's lesson.
Memorize the AWG wire table. Memorize,
Alright, next week, are we going to go over parallel and series stuff?
You want to do some of that, parallel and series circuits and things like that? Sure.
Class, but
Yeah.
you're doing all these equations with how you measure the wattage and the amperage with parallel versus series, and I find it
Yeah.
very interesting.
Yeah, that's cool.
affects switches and number of devices on a circuit, right?
Yeah,
Yeah.
yeah. When you have many devices on one circuit, and
Parallel's kind of how houses are broken. That's how houses and the wiring circuits. That's good. That's it. Because
well, yeah, yeah. Everything house wiring is parallel.
because I remember.
But remember those cheap, in the old days, Christmas lights,
Oh yeah, those are serious.
and the super inexpensive Christmas lights.
You
Uh, right, they had a series circuit, right? You had your voltage here, and so I don't know how to do the light, but they're all. That's actually a fuse symbol, but your lights are all in series, like that, right? So each one of these is a light, so they're all in series. So if any one light bulb burns out, they all stop working. And the problem is if you got, 50 bulbs, which one burned out? But those are the real inexpensive, so that's a series circuit. Those are in series.
the numbers relating between each light differ. Or no, wait. The series is the same one. Oh, the parallel stuff. It's where it gets kind of interesting, where you measure it.
Well, I mean, if it was a parallel circuit, it would be like this. All that's light, okay? They would all be like this. They would all be in parallel like this. See, if it's a parallel circuit, it's all they're all like that.
And that's where some cool numbers and stuff are. I have a notebook at home where.
Well, if all of these are the same resistance,
Right.
then the current flow in each of them is going to be the same.
But it all divides up with each wire, right?
What?
Does the current divide up every time you push it to different wires?
It does, and how it divides up depends on the resistance of each path.
Right.
So, like if this guy here is 10 ohms, and this guy is 10 ohms, and this guy is 5 ohms, your typical problem is, well, now what's going to be the current in each leg? Right. So, you got different loads here in the parallel circuit. So, yeah, that's pretty easy, that one.
I'd love to do that next time.
Yeah, because you're going to have a fixed voltage here, so you just compute those individually. Right? 10 volts with 5 ohms, 10 volts with 10 ohms, which is 1 amp, 10 volts with 10 ohms. So, yeah. So, some other things that are really interesting is transformers. And yeah, and the reason AC won out over DC back in the early days when electricity is being discovered and Thomas Edison is trying to light up the city, light up the path and he started out all with direct current DC, but why did DC go by the wayside and AC took over? And it has everything to do with transmission lines and transformers. It has everything to do with moving high amounts of power long distances. Because in order to move high amounts of power, and you don't want conductors that are the size of your arm, so you want high voltage. Because high voltage, see, like if I have a 10,000 volt source with 1 amp, I can move 10,000 watts with 1 amp. So I can have a 1 amp wire, a tiny wire.
Humans, if they're grounded properly, can touch a 10,000 volt line?
No. It's vice versa.
No. No, the reason, if you're not grounded, you can touch because no current will flow. That's why birds, we're on a different subject, but that's why birds can land on those 12,500 volt power lines and it doesn't bother. It's like static. There's no flow. There's no current flow. There's no all of these electrons stripping off. Well, what happens when you get electrocuted is all those cells get destroyed. By that current flow going through your cells, it demolishes all those bonds. It demolishes all those chemical bonds between carbon, hydrogen, and all that. When all those electrons can strip off of those molecules. So, but back to the thing about voltage and transformers is if you're transmitting power a long distance and you don't want to spend a fortune on the size of the conductor, and let's say I want to transfer 10,000 watts of power. Well, if I can have a 10,000 volt source, then I only need a 1 amp wire for 10,000 watts. I can move that at 10,000 volts with a 1 amp wire, right? You know, your wattage is equal to your voltage times your amperage. So, I mean, I could transfer 10,000, if I had 100 volts, and then what do I need? I need 100 amps to get 10,000 watts. Right? I mean, if I had 100 volts, I'm going to use 100 volts and I'm going to try to move 10,000 watts. So I need a 100 amp wire. I need I need a wire this big. But if I can get my voltage up to 10,000, now I can use a 1 amp. And guess how I get my voltage up to 10,000? A transformer. A transformer. I can't run 10,000 volts inside the generator because it's going to arc. It's going to be hard to make my generator put out 10,000 volts because of the other physical constraints of the windings and the insulation and all that. So my generator wants to be at a lower voltage because of other constraints. But as soon as I get that power out of my generator and I want to send it 100 miles, if I can transform it up to 10,000 volts instead of 100 volts, now I use a tiny transmission line. So that's why transformers took over the world, is because of the transmission problem. And so that's what they transform from one voltage to the other. And that only works because of magnetism between the primary and the secondary windings of the transformer. What's that?
Like I said, you can go either way. That's why you can backfeed a transformer. You can step it down.
They don't care. They could care less.
It'll mess you up. You can have 12 volts coming back, and all of a sudden now you've got, like I said, 1,000 volts in your hand. You're going like, uh-oh.
All these transformers on the user end are down. They're transforming down. They're going from 12,500 volts out there to 240.
But that's what they're saying is back in the areas where they have the bad storms, people would backfeed the system with their generators and kill linemen.
Oh, that's
And
cool.
the lineman would go up there to fix the pole, because you backfed it with 120 volts. Well, you just stepped it
You
up.
have to go make sure they shut off the generator.
Yeah.
Oh, sure.
Systems that are isolated
Oh.
to one actual, but people used to just you make a suicide plug, they call them.
I know. You're
To an outlet, and you power your house through an outlet. Yeah. And that's going right back to the line. But now you're supposed to have a transfer switch that opens
Yeah.
the system. Yeah. These guys would, like in Florida and stuff, would get nailed.
Oh.
Well, hey, it's down.
And it's coming the other direction from somebody put a
Oh,
generator.
it's coming from generation
Yeah.
stations down.
Yeah.
So
Yeah.
the other thing about AC versus DC is that Edison was started out making smaller devices that were using very little current and very little voltage. And as he kept going bigger, he thought DC was going to scale. And DC does really well at smaller devices and smaller levels and numbers. But AC voltage does better scaling up to higher. And he tried to scale up to the levels that AC can handle, and DC could not handle that.
Yeah.
It caused all sorts of
Yeah. Now, interestingly, in modern, oh, David's gone. I could ask him. I believe that in some of these super high voltage transmission lines that are up like in the million volt range, is they are actually using DC for some of the, but it requires a very, you can't do it with a transformer. You cannot, it's something they're doing with rectifiers and some solid state rectifiers or something. I don't understand the details of that.
Turn it almost into AC, DC into AC, or it's they chop it weird to make it like it's they make the DC look like it's AC. And the wave, you'll see it makes a wave, but it's like
Yeah.
chunky. It's not a wave. It's like blocky.
Well, yeah, it
So that's like all your
yeah, it looks like this, right? It looks like this.
yeah. I'm saying so your big photovoltaic fields, they're making power, but then they're having to convert it to alternating current to transmit it typically. But it's at a high voltage on site.
Oh, that's right. With photoelectric cells, it's all DC to begin with.
So that's the thing.
So there you got to go from DC to AC. It's much harder to go from DC to AC than AC to DC. It's much more complicated to go from DC to AC. Like in your car, when you buy an inverter, where you plug it into your cigarette lighter and you get 120 out, that's DC to AC. And that's much more complicated than the other direction. Yeah, because in the other direction you can use rectifiers, which is a diode.
So that's so everything because of our new everyone wants this clean energy. All your renewable stuff is all pretty much DC. A lot of your wind farms, a lot of your solar.
That is
So it's kinda
true.
funny that they actually now we're having to use both. You know, it's not
That's
just DC or
interesting.
AC,
Yeah,
it's both.
yeah,
All of our small electronic devices are all DC, I think, right?
yeah,
Because
yeah.
when you plug in your brick into the wall, that's converting the
That's converting the AC is a sine wave, and this is 0 here, and this is plus and minus. So in alternating current, those electrons, you know what they're doing? Back and forth, back and forth, all the way from here to the generating plant.
So it's doing this to power.
What's that?
It's doing this to power the.
To
light
what the
there.
power?
To power the light there, it's doing this back and forth, the electricity. Or he's saying
Yeah, the current flow is going both directions, all the way from the destination to the source.
not just the light. The light all the way to where the
Those electrons, man, they're on the move,
generated, yeah.
hundreds and hundreds of miles. It's almost instantaneous. This process of all the electrons hopping from atom to atom, it's almost at the speed of light, I think, in a conductor.
And that's now they're like the science. They're all like that. Sunlight is even electricity at ultra high frequency and all that stuff is what they're claiming now. You know, that sun.
Well,
The light we see is just ultra high frequency electricity. And blah blah blah. So that's why I always tell people that Jesus was an electrician first.
I don't know that no, sunlight is photons
It's just
and has no mass. A photon is a particle with no mass. See, and electrons emit photons when they drop their energy levels. That energy has to go somewhere. Energy conservation. So when certain things make an electron drop its energy level, it emits a photon.
So that's where we get light.
But a photon has no mass. Do we understand these things? No. Can we characterize them, study them, know how they behave? But to really understand it, I can't understand why that charge on that proton that's 10,000 times heavier than the electron, They both have the same electrical charge. You see what I mean? They both have the same amount of electrical charge. So the electrical charge is not dependent on the mass. So
What does the I stand for amperage?
current.
It's a French thing, I think.
Oh, I don't know where it came from. Is it a lot of these? Ampere is that guy's name.
Yeah.
Ohm is another guy's name. A lot of them
Because I know
are
like
the guys that
E for
discovered them.
voltage, electromagnetic motive force.
Electromotive force, EMF, is where the E is coming from. Sometimes that's called EMF.
Yeah.
Yeah.
I was thinking if that's what the E stands for, then what does the I? But
I don't know.
oh, in tech. And
smart computer.
I had a. It's written in my notebook back at home. I remember a long time ago I learned what it stood for. I forgot
What the what is for?
what the I stood for. It's like
Oh, yeah, we usually use it to refer to current,
right.
a measurement of current, but why is I, yeah, don't really know. So,
Yeah, amp is French, so he came up with the I
yeah,
French.
yeah, oh,
I represents intensity of current. Intensity.
oh, maybe.
Like I said,
All right.
current flow.
So, cool.
That's like for like the wattage.
We did it. It's like only 5 minutes to 3.
Thank you, sir.
I was telling him, my one to help me memorize instead of like wattage, I do P for power. So
Oh.
P equals I
Right.
times E equals pi,
That's the same.
because I gotta keep it something I can remember. Pi.
P for power. And yeah, and then you can remember the equation too.
It's like, as long as you
Oh,
know
that's
pi
good.
is-
Yeah, I get it. Pi.
E is-
P equals I times E.
I was like,
Oh, that's cool.
some of the other ones are like,
Yeah, yeah.
So, are you going to post this on the SGBC website?
We could put it up unlisted. Yeah, yeah, and then you guys can spread the link, share the link.
Yeah, we can look at it.
Yeah, yeah.
Ohm's law.